Basically, I'm talking about the SystemC Modeling Challenge at DVCon Europe 2025. For those who do not know it, it's I hope you know it of course. It's in Munich this year in October 14 to 15. We have a SystemC Modeling Challenge, and I know all of you are interested in SystemC. Maybe some of you might also still want to contribute a scientific paper. I'm making a bit cross-domain promotion here for our scientific papers. The deadline is approaching end of June, but I heard about a prolongation of a deadline. So maybe if you ask Daniel, just ask him. Maybe we can do something. Why might you consider participating in the SystemC Modeling Challenge? First of all, every participant gets a certificate that's nice for your CV, and you will present if you are winning or not something at we will have a small time slot where you can give a quick overview of your solution. You will also eventually or more or less likely win some high-end laptops that we got sponsored from Huawei. We also got a lot of second, third, fourth, fifth, and so on prizes. So I'm pretty sure that all participants will get a good prize. Furthermore, we've got funding for traveling grants. So the first submissions we get will get a traveling grant. What is now the challenge? The challenge is dealing with power estimation. Yeah. Basically, power consumption, is a new performance since years. Yeah. Unfortunately, there is no or weak or little support by SystemC directly. Directly, it's zero. If you look into the tools, it's also not fantastic. The challenge is to create SystemC model that estimates the power consumption of a small embedded system where you get some inputs of some unknown scenario, and the output of your model shall be the consumed energy, optional also the power consumption over time. I will explain a bit the use cases and importance of that. The criteria for winning is accuracy versus measurements, and maybe if you do beyond estimating the energy, some other creative features. Why power energy? Energy consumption is a key nowadays for battery lifetime of mobile devices. And SystemC models thereof can be used during optimization of hardware-related software, such as the firmware. When you optimize and play with that, you want to get a reason for power consumption and an estimation of the impact of your software changes. Another thing is that the power consumption is very relevant for power integrity. Yeah, basically, if you have a peak in power consumption or a high power consumption, you have some voltage drops, and this can cause the integrity of your saved states. Basically, your processor would crash. Yeah, you can have crosstalk, called signal industry. You can have thermal issues, heating, aging. Actually, this is all very critical in the future, even more for 3D integration or chiplets. If you can want to combine analog mixed signal processing on a chip in a housing, yeah, it will get a nightmare. And SystemC models can be very useful during architecture exploration phase. We know that. Yeah. And here the key is to characterize SystemC models such that they can predict power and energy consumption, as circuit level simulation is actually not an option if you want to do, for example, architecture exploration or optimization of firmware. Yeah, then you need SystemC. And you maybe want to predict power consumption. Now, what to do is you should register under DVCon Challenge. Your email is needed, your name, so that we can keep you updated and provide you with updated information. What you will get is a description of a small embedded system shown here. Yeah, it's a very small thing here. And a data set with some measurements of power and a small yet incomplete test bench. Of course, it's incomplete because otherwise the challenge would be finished, yeah, if we would really complete it. and via our email list some information and updates. You can send us your solution whenever you think you have something. You can join some online sessions for which we invite participants. You can also submit solutions for an intermediate review to get review, and you are allowed to do updates until October. Now, basically, what should your SystemC model do? Basically, you would get some inputs. Yeah, this is what we created, the data. You know, they are fed into our hardware prototype. And what we measured was the power as a function of T, plus some internal state here that we also protocoled together with the power. And we put that in an Excel table. And what you should then create, or basically what we provide you first of all with, is a SystemC test bench where you can plug in your model. Now, that's what you should do. Basically, for the competition, we will provide new inputs, of course, not the training data from here, but instead you will get new inputs. You would enrich here the SystemC model with some model for power estimation. You can use statistical methods, formal methods, reasoning. You can apply physical equation and somehow calibrate that, neural networks, model learning, whatever, based on the data we provide. You can also ask us for the hardware. We have a documentation of the hardware system, so you can do some more measurements if you need more data. And the objective is to estimate the power as a function of time, or the energy in sum. That is basically our minimum that you want to see. And maybe if you like, yeah, you can here use signal integrity, power integrity, noise predictions, if you like. So that would be a plus for winning or getting place one. Yeah, if you make the perfect system, but it's not expected really. Yeah, I would be happy if we have here an energy or power estimation that is more or less accurate, or gives somehow an impression of what is happening. Now I have a quick overview of the state of the art. It's a shortened version of a presentation that I made at Huawei meeting, where they invited some 10, 15 researchers from Europe, from IMEC, Aachen, Munich, and ETH Zurich. I remember also Milan, I think, was there from that motivated them to sponsor such a challenge. I will give you an overview of the state of the art. First of all, motivation is 3D integration requires power estimation. Why? Because we have the problem of heating. I mentioned that already. And here heating leads to thermomechanical issues. Yeah, that means things expand and lead to aging, mechanical aging and stress. For that reason, what currently is done is finite element thermal simulations at a very, very low level, where you really are not looking into the architecture. Secondly, we have crosstalk between layers and vias, which put power and signal integrity in question. Yeah. What one is doing today is one does circuit level simulation with RF and macro models, which again can help us to analyze corner cases, but not at a level where we play with firmware or architectures. Now for the architecture, we analysis and optimization, we might want to know about power, noise, current peaks, and so on. And the perspective could be to link system level development and circuit level to do that in a nicer way. Actually, the challenge is what we call the inverse pyramid. Yeah, because the problem with power is that the effect, the physical thing, is happening at the level of hardware, when we have a conservative system with voltages, currents, and switching. And the cause is actually not that much the hardware. The cause is typically some use case and an application in software that is running and doing something, and that switches some power states or does something. And in the end, here is where we need to optimize and here is where we need to simulate or analyze, and that is really a challenge. I have here an example from the past where we did some research. I don't go into detail. It shows that, for example, if you have here some vehicles driving around each other and they have tire pressure metering systems, and you want to analyze the power consumption of the wheels here, of the tires and the senders and receivers here, you would need that to optimize battery lifetime. Yeah, you might want to optimize the protocols, you might want to optimize the firmware and so on. And you might also not want to do that with hardware prototypes or SPICE. Now let's give me a quick overview of the fundamentals of power estimation. That's what I'm here. Basically, if we look at the physical lowest layer, yeah, what we see here, if we have digital circuits, we have a dynamic power consumption and a static power consumption. The dynamic power is due to charging of capacities and short circuit of the CMOS switches, and the static is due to leakage, tunneling, and some other effects. We can estimate that with some simple formulas that are given here by Litzk and Rabai, and also some equations here. What you can then do is you can play with the supply voltage, the clock frequency, and reduce the switching activity, or you can play with your PDK and reduce here the load capacities. Here you can reduce the supply voltage, basically power down or slightly reduce it. That helps. And you can also reduce the temperature, which goes very strongly here into that power consumption. However, in the end, that would require a post-synthesis. That means gate level power aware simulation. That is also state of the art. You can do that with circuit simulators where you basically know the number of gates you are using for CL. The supply voltage is known, the clock frequency is known, and you count events and activations of gates to determine alpha. And then you can roughly calculate here some power consumption. What you would get is an accurate power consumption in the ranges of plus minus 10 to 20%, which are the best values reported in literature. The disadvantages is that it is simply too slow to be useful. Yeah. For example, if you want to simulate a scenario of 20 seconds with multiple processors, I would say simply forget that. Yeah, if you want to finish in before the whole chip and project is finished. Also, it's too late in the design flow. Actually, if you want to optimize architecture level, you might not want to rely on some gate level implementation. Then it's too late simply. It's also limited to digital parts. We sometimes, or in our use case, have PLL, transceiver, and so on in an embedded system. If you look at it from software, we find some power management strategies that do a frequency scaling, run fast and stop, dynamic voltage scaling, or adaptive voltage scaling, where frequency scaling adapts the clock frequency, run fast and stops makes power down or optimizes the power down times. Dynamic voltage scaling adapts the clock frequency and at the same time the supply voltage, both together. And adaptive voltage scaling adapts the clock frequency, the supply voltage, but considers also process and variations and temperature. All this is in the end controlled by the software. And again, we have here our inverse pyramid. The software controls, and here we see actually at the physics together with the formula what is happening and where the cause lies. The nice thing, which simplifies our life very much, and I think this is a good hint for solution, I will introduce a bit the state of the art very soon, is that we have so-called power statements in all of the power management strategies. These power management typically switches here these parameters to different component power states. That means it sets the clock frequency and the supply voltages for parts of the system. Some can be power down, some power up. we can have supply voltage changes and clock frequency changes. Yeah. Note, for power estimation, we use the same terminology of power state, but with a slightly different meaning very soon. Yeah, for power estimation at system level, we use power state machines, short PSM, and this is what is given. Basically, we have operating states. Here, this is from the original work from Benini et al. 1998, where we have, for example, here a simple model for a backlit, a display, and display power that change depending on the operating mode. We can label the states, the operating states, with some power consumption, as you see here. And then we can just, once we have estimated these numbers, we then can switch between the different states if we observe some inputs and then sum up here the power consumption. The same, by the way, works for microelectronic systems. For example, memory access here by Bernini et al. 2000. And of course, it can be improved. Yeah, the improvement is then called power state transition machine that also labels the transitions with an energy. So if you go from backlit to display off, you would maybe consume some work or energy. You can further extend that, as was done by my PhD student, Xiao Ban. He extended the power state machine such that it can also predict some signal or power integrity issues, as you can see here. Yeah, you see very close what was measured or simulated with SPICE, and here predicted by the SystemC model. Basically, the idea is here to label the transitions also with differential equations that get a step response, and we characterize the output then accordingly. Also, we add here some noise and colored noise to the steady states to reproduce the thing more accurately. Now you can do then some power simulation at system level. This is basically what we are doing in the challenge. Yeah, and we don't need a lot. I'm talking here about an ISS in the slides, but you don't need it. You simply don't need it. Yeah, because the only purpose of the ISS is here to get the points in time when a power state changes. Yeah, that's basically all. Yeah, and all we have is in the principle a scenario that is characterized by a sequence of state changes of the operating states. That's all we need. We don't need an instruction set simulator in our competition. In practice, you will get that sequence by an ISS. We don't need it. Yeah, it's a simple, very, 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 very simple SystemC model that plays a sequence of operating states. Yeah, what one can do is one can here instrument an ISS with a monitor that traces the state changes over time, and then we can here sum up the power in each state. Yeah, of course, power multiplied with time, and we would get the energy, or if you trace that over time, maybe plus the state changes and transitions, you would get then what is the trajectories of power consumption. You can play a bit more with that in order to here also allocate because what was done here, yeah, this will only allow you to estimate power, but that's not very useful. Yeah, imagine you have a software that runs in your virtual mobile phone, and as a software developer, you get said, okay, it's from 21 to 20 joules. It has been optimized, and you might want to know why. Well, but then the pure number of energy consumed is not useful. You would see here the power consumption over time, and you would be able to analyze here the analysis of power states, the duration, and hence you can predict the power consumption. But that's not helpful for a software developer. For a software developer, what he wants to know is how much power is consumed. Clear, we can answer that. By which hardware element? Okay, we so far can answer that too. But for a software developer, we want to know why was the energy consumed. So basically, we want to know, like in a debugger, which software activity has triggered the use of consumption. Yeah, hence we can further instrument our software with activities and allocate messages so that we can learn about here which of the software routines we have written has contributed or caused some state changes, and can then optimize and fix that. Yeah, we did that for an example. I dropped that for the sake of time and come to a quick outlook. I make it again a bit shorter. Just as a reminder, I have talked about a lot of state-of-the-art, scientific state-of-the-art. What we have in the competition is at one hand more challenging because it's not that simple because of the embedded system has a lot of practical challenges. Yeah, we have real world measurements that are with a lot of noise. And what basically you could do as a starting point is a power state machine. Yeah, Moritz has already provided you here in the examples a very simple framework, very simple. You can extend that to an extended power state machine, or you can add a power state transition machine, or you can use machine learning and so on to learn a bit more on predicting the whole power and energy consumption behavior of our little embedded system. You can now join and register under this link as shown here. We will provide support if you have questions. So imagine you have still some questions, just send us a message. You will get feedback and help for understanding, or if you have already a preliminary solution, you can just send it in. We will check, give you feedback. We can also, if you think that our measurements are not enough, they are indeed not that huge as you might need, for example, for some machine learning approaches, then we can assist you in getting the hardware. We have some of these embedded controllers. They are not expensive, by the way. Yeah. And the nice thing is they have internal power measurements, so you can also directly get the power measurements, which otherwise would be really a challenge. Yeah, so we can provide also the hardware and additional measurements to you. So far, I have added here a few references if you want to read that. We will provide these slides on the website to all the people that register there. And yeah, I would just invite you to register under this URL. Yeah, it's just a small form where you can register. We provide the additional information and you can also access the measured data. We will provide also updates to it. Many thanks. Are there questions?
Christoph, the information is brilliant, and I hope that people do indeed participate, because there's some pretty nice prizes on offer, if I understand correctly.
Yep, prizes are top-notch notebooks from Huawei, some Huawei watches, or it goes down, yeah. But it's quite good prices, yeah. Plus, if someone is interested, let me know. We can provide traveling grants. We have a budget for that. Let me know.
Okay, yes, good point. This is obviously for DVCon. So if you are a student and you'd like to go to DVCon and you need budget, then please get in touch with Christoph.
Yep, we will appreciate students, but also PhD is a nice thing. If you are a PhD, you can, of course, also participate. I think the only who should not participate are my PhD, for obvious reason. Yeah.
And maybe people who have written SystemC AMS, not looking at anybody in particular, but they might be excluded. I don't know.
Yeah. I think
But
the
it's
only one I
certainly
would
something
clearly exclude is Moritz and members of my group.
it's certainly something that if you have students or you're in academia, for instance, and you want to pass this message on, then please do so. Are there any other questions for Christoph? In which case, excellently, 10 minutes early, we'll move across to Sarah, if we may.